Okay, this is where we are finding the wave function, the equation of motion for the particles on the string. So we are looking for an equation y as a function of x and t. So what this is it's a function that's going to describe the displacement on the y-axis depending on what particle we're talking about on the string, like the particle's position on the x-axis, and the time that we're referencing. So if you imagine this as an animated system, it depends. So if we're looking at this guy right here, it depends how far along the x-axis he is for his displacement. And it also depends on what time that we're talking about, because as time moves on, this rope begins wiggling. And so it's a function of both of those quantities. And in the end, we're going to get the particle's displacement. So if you remember in the beginning, I said there's two things that we're interested in with these waves. One is the energy that's transported and propagated down the medium, and the other is the displacement of the particles. And so we're going to get an equation of motion that describes the displacement. And with the displacement, we can take some derivatives with respect to time and find the velocity and the acceleration of these particles. And we can take derivative with respect to x and find the curvature, the slope and the curvature with the second derivative with respect to x of the string, and we can do some stuff with that. So where do we start? Well, we know all about periodic motion, and so if we consider a point at x equals 0, then it should be no different than our harmonic oscillator, right? So we have at x equals 0, we have our wave function must take the familiar form a cosine omega t. So we're close. You could say we're halfway there, because now we have a function that depends on t. We just need to get x in there somewhere. All right, so how do we get x in there? Well, remember that this wave travels at a wave speed nu. This is not the speed of the particles. It's the speed of the wave, the disturbance that propagates through it. But what this means is we can say that it travels a distance x from the origin in an amount of time x over nu, right? That just defines the speed. So this is like meters divided by meters per second, and so you're left with seconds. So that is time. So it travels a distance x from the origin in an amount of time this, right? And so we can say, since wave speed is defined by wavelength and frequency, we can say nu equals wavelength times frequency, that the position of a particle's displacement begins to repeat after a full cycle of time. And a full cycle of time would be x over nu. So therefore, the motion of the particle at any point at time t is identical to the motion of point x equals 0 at the earlier time t equals t minus x over nu. So what we're saying is if we look at a particle at x equals 0 and we let it cycle through an amount of time so that it comes right back to where it started, so it'll go just like I've drawn here. It'll go up, say, and then it'll go back down and it'll come back to where it is. So we're not tracking through x, we're just looking at a particular particle through time, one full time cycle. And so the position at any given x is identical to that same x at one time cycle forward. And we've defined a full time cycle in terms of x here, of x and nu. And so we can insert this into our wave function, our working wave function that we left off with here, and get x into our equation. So what we're saying is y at any x for a given t is equal to a cosine omega, and instead of just t, we're going to insert this here, t minus x over nu. Do the square brackets here to keep it neat. Do you follow that? All right, so then also, since cosine of a negative angle is equal to cosine of that same positive angle, we can switch the order here. Y of x and t is equal to a cosine omega x over nu minus t. And because omega is defined, I'll do it on the next line, omega is defined as 2 pi times the frequency, we can insert that in there and say y of x and t is equal to a cosine 2 pi f x over nu minus t. You follow? So this is a wave function. So this totally works, and this one, for that matter, is as well. From here, we can just kind of manipulate it a little bit, given some known equivalencies, and we can get it into useful forms depending on the problem. So, for example, you can get it in terms of the period t and the wavelength lambda. I'll let you prove this to yourself, but you can get it into the form here, a cosine 2 pi x over lambda minus t over the period. So that could be useful. The most common expression for the wave function, however, involves a quantity called the wave number, and that is denoted with the letter k, and we are defining, I can do that, defining k to be 2 pi over lambda. That's the wave number. So, if we substitute two things into the definition of wave speed, so the wave speed, nu, is lambda times frequency, we have an expression for lambda and an expression for frequency. So lambda is equal to 2 pi over k, right? Just rearranging them. And frequency is equal to omega over 2 pi. So given those things, and putting each of those in here, then we can find the angular frequency, omega, in terms of the wave speed and the wave number. And this is going to be very useful for coming up with a compact form for this wave function. So make sure and prove that to yourself. Go through the quick algebra to make sure that you're following what's going on. Make sure that I didn't make any mistakes. So if we put this into our wave function, we can get it into the form, and prove this to yourself, please. Y of x and t is equal to a cosine kx minus omega t. This is the form that you will see everywhere. It's compact, it involves useful quantities for a wide range of applications. We're going to call this our wave function. So we did what we set out to do. we have an expression for the amplitude of any particle, or the position of any particle, that depends on x and t. So from there, we can find the velocity of the particles, and this, remember, is the velocity of the particles, not the wave. So it's the transverse velocity up and down as a wave pulse goes through, by simply taking the derivative, or in this case partial derivative, with respect to time of this function. So Vy, function of x and t still, is equal to the partial derivative of y as a function of x and t with respect to t. And so the omega comes out, negative sign, a sine, same function, kx minus omega t. So that's the velocity of any given particle depending on x and t, its x position and the time that you're talking about. And then acceleration would be just another partial derivative. So ay, x and t, is equal to the second derivative with respect to time, which would be omega squared. Negative sign comes out. A cosine kx minus omega t. And since this portion right here is just our original wave function, we can write it as negative omega squared y x t if we like. We can also go the other way. Instead of talking about the speed of the particles up and down, we can talk about the curvature of the shape of the string as a wave passes through at any point in time t and at any place along the x-axis. So that would be looking at this literal function here and just taking the derivative of y with respect to x. Very familiar thing. And so we can do that here. Ooh. I'm going to skip right to the second derivative to talk about the curvature because that's what we need. So the second derivative of y as a function of x and t with respect to x is negative kx squared, negative k squared, a cosine kx minus omega t. Or, again, negative k squared, our original wave function. There we go. All right, so we're going to look at each of these two partial derivatives here, this guy and this guy. So remember that omega, we said this just before, omega is equal to nu times k, right? So if you divide this guy divided by that guy, you'll notice these terms are the same, right? So what I'm saying is, if you divide d squared y x t dt squared divided by d squared y x t with respect to x, then what you get is this term divided by that term, but these two things are the same. So you would get negative omega squared y x t divided by negative k squared y x t. So those cancel, the negative signs cancel, and so what you're left with is omega squared over k squared. Well, omega over k is equal to nu, and so this must be equal to nu squared, the wave speed squared. So therefore, if we do this, we should find that if you bring this guy over to the left here, how do I want to write this? Well, here, I'll write it down and then you can verify probably by inspection the algebra real quick. So partial derivative of y, x and t, divided by dx squared must then be equal to 1 over nu squared times the partial derivative of y with respect to time. Make sure that you followed that last step there. This is even more important than the wave function. This is called the wave equation. And it's one of the most important equations in all of physics, because it's not just valid for waves on a string. It's not just valid for sinusoidal waves, period. It's valid for any wave. So let's study it for just a sec before we end this video. Let's make a plot. Let's make a plot. We'll make two plots. One is looking at what the particles are doing, what velocity and acceleration they're experiencing. So this is y and this is x, and we have a wave that is moving. Oh yeah, let's also define, this is peak amplitude, peak negative amplitude. So let's say we have a wave going like this, and we're going to look at various particles here. All right, so let's talk velocity first. So the wave is traveling this way. So that means that each of these little disturbances here, and so on, are propagating to the right. So if you are this particle right here, what's coming next is you're moving up. You're going up this way, buddy. And so velocity is upwards there. Same for here, Vy. Same here. Here, it will be moving up, but at this moment, right at the bottom, there is no y velocity. For a moment, it stays at the bottom, right, as that trough rolls through it. And then, if you think about being this particle right here, and this wave is moving this way, well then you're hitting the trough next. You're rolling down. You're on your way down, and you're going to become the trough next. And so all of these are on their way down. And then this guy again, momentarily, he's at the peak, and he is not on his way up or down. So that's what's happening with velocity. Acceleration, this guy is moving up, but he's slowing down as he's moving up because the acceleration is downwards there. At this point here, you have max velocity, and so and that's because the acceleration ay is 0, and on this point, the next point, the acceleration is up. So it's speeding up here, and then slowing down. Yeah, that's a better way to write that. I guess with our arrows, you can kind of probably infer. So it's speeding up as you're traveling along this way, and then it's slowing down on this portion of the curve. Hey, don't do that to me. There we go. This is positive acceleration. Even though its velocity 0, its acceleration is still up. You remember that from projectile motion, maybe, where it pauses in terms of vertical velocity at the peak. And then here, AY is up still, because in this case, the velocity is downwards, and the acceleration is slowing it down. And here, acceleration is 0, and here it's negative, and here it's negative. So let's make more sense of the acceleration. Why is the acceleration pointing the way that it is, independent of corroborating it with the velocity? Well, the acceleration comes from our restoring force, right? And our restoring force is there because it's away from the equilibrium position. And so the restoring force is always trying to bring us back to equilibrium. And so you can see the pink arrows are always pointing back towards that flat line. And that provides our restoring force. All right, so let's now look at a second plot and then be done with this section. So a second plot where we step through time. Here we go. All right. All right. So this is still x, and this is still y. This is still going to be peak amplitude, peak negative amplitude. And we're still going to have this first wave here. But we'll say this is at time t equals 0. If we were to step forward just a little bit in time and animate it just a little bit forward and then pause it again at 1/20th of its period, or something close to that, then you would get it just a little bit ahead. You get a wave like this. And remember, it's not the particles that are moving to the right. This particle has not moved to become in this forward advanced space there. This particle here has moved up to become this particle, right? And this particle has moved down to become this particle. All of the motion is transverse, and the direction of the wave propagation is yet along the x-axis. That's a transverse wave. All right, so that ends this section. Next, we're going to talk more about the wave speed. We're going to use our wave equation.